Okay, so we'd left off with this fairly classic problem, the elevator problem. The elevator accelerating up. We're told we have a 75 kilogram person standing on a spring scale. So that's going to be affected by the acceleration of the elevator. We're told during the first 3 seconds of motion from rest, the tension in the hoisting cable of the elevator is 8,300 newtons. And we'd like to find the scale reading of the 75 kilogram person standing on the scale if the system mass is 750 kilograms. So we introduced this one last time. We'll go ahead and go through the solution. I'm going to look at a free body diagram of this thing. That'll help me with the system. So if I look at the entire elevator, so I'll draw this elevator. We then have the scale. We have the person standing on the scale. And we're told that the tension in this lifting cable is 8,300 newtons. This would have some weight, okay, which would be equal to mass times the acceleration of gravity. And quick calculation, if it's 750 kilograms, we'd know that it's accelerating up because this 8,300 is greater than that 750 times the acceleration of gravity. So I'll go ahead and put my acceleration over here. I'll take it as up. Had I made a mistake on that, I'll just get a negative number in the acceleration. Well, let me look at this. If I take the system mass, which is 750 kilograms, and I multiply that by 9.81, the acceleration of gravity, we come up with 7,360 newtons, which is definitely less than 8,300. So again, our assumption that it's that it's accelerating up, I think, is a good one. So what I'd like to do then is I'd like to, for this elevator, I'd like to sum the forces in the vertical direction, setting them equal to mass times acceleration in the vertical direction. And we can say if we take positive up, we could say that the vertical forces is 8,300 minus then this weight that's acting down, 7,360, is equal to the mass. The mass of our system, we're told, is 750 times the acceleration A. So if we go through the solution of this, one unknown in that expression, the acceleration A turns out to be equal to 1.257. I got too many significant figures, but I'll leave them since it's an intermediate step, meters per second squared. So that's the acceleration of the system. It shouldn't surprise us that it's up since the force in the hoisting cable is greater than that 7,360. So what I'm going to do is I'm going to take this acceleration here and I'm going to go over and I'm going to draw another free body diagram. So we have this person standing on the scale. And we're told that that person is 75 kilograms, so there's some weight, which would be 75 times 9.81. Okay, that's their weight. And we have then the force of the scale pushing back on them. So that's what we're looking for. We know that the acceleration, the system is accelerating, so this person would be accelerating. So we'll put their acceleration there. And it would have the same acceleration as the elevator. We don't think that they're going to go up and bump their head in the elevator or something like that. So if I look here, summing the forces in the vertical direction, setting it equal to mass times acceleration in the vertical direction, and I'll go ahead and take a positive up again here. We could say that we have the force of the scale pushing on the person, minus this the weight, which is 75 times 9.81, is equal to their mass, which is 75, times the acceleration. Well, the acceleration, we'll take that as the acceleration of the system, 1.257. So we can solve for the force in the scale, the force the scale is pushing on the person with, and that turns out to be equal to 830 newtons. So the spring scale would read 830 newtons. And if you look at this equation here, you could really come and rearrange that mathematically and say that the force on the spring scale would be equal to this 75 times 9.81 plus 75 times, if you will, the additional acceleration, right? And if I were to factor that, I could say that the force on the scale is equal to 75, that's the mass, times 9.81, that's the acceleration of gravity, plus the acceleration. Okay. So really this would be a lot like standing on a planet that just has a higher acceleration of gravity, one in which its acceleration is going to be 9.8 plus 1.257. So sometimes people will move things to the other side of the equation. Don't let that confuse you, because mathematically we have exactly the same thing going on. Questions with that problem? So oftentimes we'll have to draw a couple free body diagrams. Yes?
So does this only work when it's accelerating upward? Like if it reaches constant velocity, would the scale still be
Well, during the first reset, it only works if we have that constant tension in the cable, which leads us to the constant acceleration. If at some point you stop accelerating and go back to some constant velocity with zero acceleration, then yes, it's not going to be the same problem. I mean, with constant acceleration, this is a fairly easy problem. Let me carve this out here. So say the acceleration is equal to 0. That would be no acceleration, right? Okay. Then you're going to have that F sub s is equal to 75 times that 9.81, or is equal to mass times the acceleration of gravity. So yeah, this only works while you're accelerating. If it was a very tall building or something, at some point you would probably stop accelerating. Other questions? Okay. So the next problem has a couple different directions involved in it, a little more complicated equations, a little more complicated free body diagrams, so it's a good transition. We have a system here where we have this 400-pound log that's being pulled up a ramp. It's pulled up with a pulley system, so there's a pulley here. We have a cable that's attached at this point. It goes around the pulley that's attached to the log, back around this pulley, and is hooked to some counterweight A that's 250 pounds. The coefficient of friction between the log and the ramp is 0.5. The ramp is 30 degrees up with respect to the horizontal. And our counterweight here, you can imagine this thing is being held at this point, and when we release it, it's 20 feet above the ground. And what we'd like to find is the velocity of the log. How fast is the log going up that ramp when the weight hits the ground? You could imagine the weight coming down here and hitting the ground. And we'd like to know how fast the log is going when that happens. So in all of these kinetics equations, we always start them the same way. We always start them with a free body diagram. So I think I'll look at the free body diagram of the log. So looking at a free body diagram of the log, we have I'm going to have some tension pulling it up, and I think if you were to cut through this cable right there, whatever tension you had in the cable, this would be twice that tension, wouldn't it? Okay. And then I've got the weight of this thing acting to the center of the earth, so I'm going to take this as 400 pounds acting down. We'd have the normal force, that's the ramp pushing back on the log. There's the normal force. Incidentally, this angle in here ends up at what, 30 degrees? And then the friction force is opposing the motion, so we have the coefficient of friction mu times the normal force n. Okay. The last thing to do is to establish acceleration, and I could say I think it's pretty hopefully obvious that it would be accelerating up. So I'm going to put some acceleration here. I'm going to say that this is the acceleration, and I'm going to divide it by 2 because I want to talk about that weight A accelerating down at A. And we would see a 2-to-1 ratio for this. And you can actually do this as when we finished up with our material from Chapter 12. If I draw a quick little diagram of what's going on here, we have this pulley going to the log, and then it's coming back around this one, and it's going to A. So we have the log here, we have A there. And I could talk about some distances. I could talk about this distance being what S sub C, and maybe I'll talk about this distance here being S sub A. And I could then talk about the length of that cable as 2 times S sub C plus S sub A plus some constants in there for the pulleys, circumference of the pulleys and things like that. So if I differentiate this, I get 0 is equal to 2 times S sub C dot plus S sub A dot. And again, I would get 0 is equal to 2 times S sub C double dot plus S sub A double dot. So we can relate that there's a 2-to-1 ratio on the acceleration, right? The acceleration that we get here at A is going to be related to the acceleration at C, or the acceleration of the log, by a 2-to-1. Okay. Most of you probably don't necessarily have to do that, but if you wanted to prove that to yourself mathematically, that's how you do it. Now I have quite a few unknowns in this picture. I have the acceleration as an unknown, I have the tension as an unknown, I have the normal force as an unknown. So I think I'm going to have to end up drawing another free body diagram. Before I run off and do that, let me put a coordinate system on here. I think I will go with a coordinate system that is x up the ramp and y perpendicular to the ramp. And I'll then draw a free body diagram of the weight of A, which is a little simpler. So if I said this was 2t, this would have to be just t, wouldn't it? And while we're on that vein, we could talk about the acceleration of this thing. The acceleration is going to be down, and if this is the acceleration over 2, this would just be A. I've got some weight here. What's the weight on this? 250. Anything else? I think I've got that. Okay. So let's see. We've got another equation in the vertical direction where we can relate the tension and the acceleration. I think we've got a shot at this. So coming back over here, if I sum the forces in the y direction, setting it equal to mass times acceleration in the y direction, what acceleration in the y direction do I have? Hopefully 0, right? I mean, we're hoping the log's not bouncing up and down as it's going up that ramp. We're hoping the acceleration there is 0. So I could say then, and I'll go ahead and take positive away from the ramp, I would have the normal force. So this is positive. I'd have the normal force minus, what, 400 times the cosine of 30 degrees. Anything else in that direction? Nope. So that's equal to 0, so I get a real quick equation that the normal force is equal to 400 times the cosine of 30 degrees, which gives me 346 pounds. Okay, so that's an important intermediate step, because when I go on then to sum the forces in the x direction, I'm going to need that for the friction. So let me do that. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. Here I'll go ahead and take up the ramp as positive. And I have 2t, that's going up the ramp, minus mu times n, that's going down the ramp, minus 400 times the sine of 30 degrees. Okay, that's the component of that weight down the ramp. If we look at that weight, it has two components, that one there and that one there, doesn't it? And this is then equal to the mass. What's the mass of that log? This is where you have to be real careful. This is a force, isn't it? So the mass of that is going to be 400 divided by 32.2. That turns that into a slug. That turns it into a mass term. And its acceleration is, according to this, if I take positive up the ramp, the acceleration is a divided by 2, isn't it? Now make one more substitution here. We know that the normal force N, that's 346. So I have one equation with two unknowns. Okay. So I'm going to call this equation 1. And hopefully I can get another equation with the same two unknowns. Let me come up here and talk about some of the forces in the vertical direction is equal to mass times acceleration in the vertical direction. I'll do something a little different. I'm going to go ahead and take positive down. There's nothing that says that I can't do that. So I will have 250 minus T is equal to the mass, which will be 250 divided by 32.2 times the acceleration, which is A. Okay. So with this, I have equation number 2. I have the same unknown tension. I have the same unknown acceleration. And I'm going to then solve equations 1 and 2 for the tension T and the acceleration A. When you do that, and it's pretty straightforward with that. We want to go through that. Everyone's okay with that. You put them in a matrix. You can do substitution, simultaneous. So you'd come up with the acceleration A is equal to 5.83 feet per second squared, and the tension T is equal to 205 pounds. The acceleration is always a little hard to figure out whether it's right or wrong. The tension's quite a bit easier. If this is a static situation, if it wasn't going anywhere, what would the tension be? 250. That weight is falling. Do we expect the tension to be greater than or less than? Be less than, wouldn't it? Okay, that's like you getting in the elevator and pressing the down button. You weigh less in the elevator when you press the down button. So I think that tension is good. I think that we can trust the acceleration. We're looking for the velocity of the log when it hits the ground. Okay? So I could come over here and say then that we have velocity 2 squared is equal to the velocity 1 squared plus 2 times the acceleration times the displacement. That was our kinematics equation, right, for constant acceleration. This is constant. So I could solve then and say that the velocity then is really just equal to the square root of, what am I going to have, 2 times A times the distance s, right? So I've got then the square root of 2 times our acceleration, which is 5.83. Now, is that the acceleration of the block or the log? That's the acceleration of the block A, isn't it? And that's probably, I mean, we could have done this a little bit differently and said that this was T and this was 2T and then this was A over 2 and this was A, and then I would have had to have been careful there. But this is probably a reason for naming this A. What's that? Well, if we took this as A, this would be 2A. Yes. Yep. Sorry. Okay, so I got the acceleration there. And then the distance, how far is it going to drop? 20. So we come up with, when you go through that, the velocity here is 15.3 feet per second. Now that's the velocity of what? That's the velocity of block. What are we looking for? The velocity of the log. So what's the answer? Half that. Yeah. So the velocity of the log is going to be equal to half that, or half of 15.3, about 7.5, 7.6, something like that. So it's important in these systems where you have these ratios of velocities and acceleration that you keep track of what you're looking for and what you are using. And in the end, probably the most difficult part of this problem is to have the discipline to just keep drawing free body diagrams. When we get down here, to this one, and we realize that we have too many unknowns, we've got to go draw another free body diagram to get the solution. Questions with that? Remember also, if you've defined that you're going to take positive down, 250, that was down, so that's positive. T was up, so that's negative. Then what about A? A was down, so it becomes positive, doesn't it? Our sign convention that we use on the left-hand side of the equal sign has to be the same as the sign convention on the right hand. Yes?
So you're allowed to change your coordinate system between two free body diagrams and a rotated one to the positive down.
Yes. Yeah. We wouldn't want to change our coordinates here in this one, but as we go to another one, you can change them. Yes. And that's in fact why I did that. Yes. Yeah, they're only related because of the tension and acceleration. Well, the next set of problems we're going to deal with a curvilinear motion, things not moving in a straight line, so starting to move around some sort of a curve. And if you remember our conversation in kinematics, we looked at breaking curvilinear motion into three pieces, or analyzing it with three different coordinate systems. A rectangular system. So if things were given in x and y, it seemed advantageous to look at it in x and y. You simply say the sum of the forces in the x is equal to mass times acceleration in the x, and sum of the forces in the y is equal to mass times acceleration in the y, where your acceleration in the x would be x double dot, or the acceleration in the y would be y double dot. I mean, this is good. We don't use these a lot. Probably the one that we use the most is normal and tangential, where we just say the sum of the forces in the normal direction is equal to mass times acceleration in the normal, and the sum of the forces in the tangential is equal to mass times acceleration in the tangential. And then we have to talk a little more about, well, what's the normal acceleration? That's v squared over rho, or v squared over r if you have a constant radius. We could also write that as rho times theta dot squared, or the velocity times theta dot, where theta dot's equal to omega. Okay, so we'll see this. And then in the tangential direction, that's just the change in the velocity. A lot of times, if you have constant velocity, you have no tangential acceleration. Or we could say it was r theta double dot, where theta double dot is equal to alpha, and we'll see that again. So that's a pretty common one. Polar, sum of the forces in the r direction is equal to mass times acceleration in the r. Sum of the forces in the theta is equal to mass times acceleration in the theta. And then what's the acceleration in the r and the theta? That was those long pieces that you probably want to put on your formula sheet. They're a little bit hard to remember. We derived those when we were going through that. Now, a lot of times we'll actually use these in conjunction. We might use normal and tangential and rectangular. As if you look at a car going around a racetrack, you have normal and tangential, but then you have a mutually perpendicular direction that you might want to deal with a rectangular coordinate system. So there's nothing that precludes us from using a combination of these on the problem. And it's fairly common to use a combination of rectangular and normal and tangential. Okay, so those are the systems that we're going to use. Okay, I'll be posting the PDFs after class. Okay, so I'd like to look at this problem here. This is our, we've got some sort of a tub here. You could simulate this on the washing machine. If you jam a screwdriver into the lid safety switch, you can probably do this. Hypothetically, jam a screwdriver into the lid safety switch, you can simulate this. Okay, and you can get the washing machine up on the spin cycle. And what we'd like to do is, with this thing spinning around, so this is like the tub in your washing machine spinning around, and it has some angular rate omega, which that would be equal to, remember that omega is equal to theta dot. So it's spinning around and has some radius r. We'd like to figure out how fast this has to spin, what that omega has to be to keep that block from sliding down. And the friction between the side here and that block is given as mu. So we've got everything in the abstract here. It should be kind of interesting as we go through this. You probably had more experience with this in another context rather than having experiments on your washing machine. There's an amusement ride at a lot of fairs and whatnot where you come in and people stand on the side here, right? and the floor is there, and then they get you spinning, and all of a sudden they drop the floor out, and you're supposed to be terrified that you don't go falling down with the floor, right? Have you seen those at the fairs and whatnot? Have been on them? Okay, great. Okay, good. So whether you're doing some experiments with a washing machine, or whether you call on that experience from the fair, hopefully you have some context for this. Well, let's see if we can work our way through this. First of all, again, just because we looked at, had this different slide here with curvilinear motion and saw some things that we had seen back in kinematics, doesn't mean that we're changing anything. We're still in kinetics, we're still dealing with forces, and because of that, I still want a free body diagram. So let me draw the free body diagram for this block A. So that's that block A, or that's what you look like in the machine if you were to be approximated as a block. Okay, what forces do we have here? Well, you certainly have your weight, don't you? mg acting down, and you have the normal force here. Is that right? Anyone that's been on that ride, you got that thing's pushing on your back, isn't it? You stand there, it's definitely pushing on your back. That's what's pushing you around the curve as you go through that circular motion. Okay, a lot of people like to have a force in this direction here. Okay, a force to your right. You're not going to have that. Okay, you got that normal force. What about an acceleration? Are you going to have an acceleration? Absolutely, you have an acceleration. You have an acceleration in the normal direction that's equal to v squared divided by rho, the radius of curvature, right? You could call this the centripetal acceleration, and you know the acceleration is on the opposite side of the equation in Newton's law, so if you wanted to, you could come back and put this force going the other way. That's what they come up with, that fictitious force, the centrifugal force, right? That's really wrong. They should call it centripetal acceleration. But I guess it's easier to describe how water stays in a bucket when you swing it around to a second grader if you have centrifugal force, right? There's no such thing. You have centripetal acceleration. You look at this acceleration here. And we've got some problems coming up that I will address that more clear if you're still a little bit foggy on that, although I suspect they've cleared up much of that in physics. The last thing, I think we've got friction, right? This thing only works with friction. So we've got the coefficient of friction here, mu, times the normal force n. Anything else? We've accounted for your weight. We've accounted for that friction. Usually there's some kind of rubbery coating in the thing that you see at the fairgrounds that provides good friction. And we've got the normal force n. So why don't I go ahead and take a coordinate system. I could go ahead and take a coordinate system that looks like this. I'll take x this direction and y that direction, just so we have something to talk about. And if I sum the forces in the y direction, setting them equal to mass times acceleration in the y direction, what do we have? What's the acceleration in the y direction? Yeah, we're hoping it's 0. We're hoping you're not going to slide up or down. Hoping that's 0. So I could say then that the force in the y direction is mu times n. I'm going to take up as positive, so I've got mu times n, that's acting up, minus mg is equal to 0. Okay, so I could say that the coefficient of friction times the normal force is equal to mass times the acceleration of gravity. And I'll leave that like that. We'll come in and probably use that for a substitution. Now I'm going to talk about the sum of the forces in the x direction is equal to mass times acceleration in the x direction. And I mean, if you wanted to, you could turn this thing around and you could talk about, well, I want to do the sum of the forces in the normal direction is equal to mass times acceleration in the normal direction. That would just mean that I was going that way, right? Here I'm just going the other way. I'm still going to assign it the same acceleration. So what do I have for the forces in the x direction? Minus n. Anything else in the x direction? No. Okay, so minus n is equal to the mass times, what's my acceleration in the x direction? Minus v squared over the radius of curvature rho, right? I got a couple negatives in there, so I probably would have been better off thinking about this, right? Or at least taking my x direction the other way. But I wanted to show you that either way will work, as long as you're consistent. So I can say then that my normal force N is equal to the mass times v squared divided by, I'm going to say this rho, that this is r. So I have v squared over r. Okay, so I multiply it through by -1. And maybe I'll work this one just a little bit more. I could say that the normal force here is equal to mg divided by the coefficient of friction mu, right? And I will substitute that then into there. And I have that mg over mu is equal to mv squared over r. And I get to cancel the masses out of this. Okay. The mass didn't matter. How many people have done this at the fairgrounds? Okay, a few. Did they line you up and the light people went with a small mass went first, and then after they got done, the people with a middle range of mass went next? No, your mass did not matter. Okay, so mass didn't matter. So what do we got here? We'd like to find the minimum omega. I have a great equation, but I don't have omega in it, do I? I found something. I made some great discoveries, but no omega. So let's see. Can we figure out what's omega equal to? I know that the velocity is equal to omega times r, right? Okay. So velocity squared is going to be equal to what? Omega squared times r squared. So I substitute this in. I can say then that g over mu is equal to omega squared r squared divided by r. I get to cancel that with that. And I can say then that omega, solving for omega, is going to be equal to the square root of the acceleration of gravity g divided by mu r. Okay. So that's the velocity you need. It has to do mainly with the coefficient of friction and the radius. Now, what do the units look like in this thing? If I, underneath this radical, if I have English units, I'm going to have what? Feet per second squared for the acceleration. Mu does not have units. R would be presumably in feet. Is that right? So I get to cancel that, and you take the square root of 1 over second squared, and you have 1 over seconds, which is radians per second, right? Radians per second. So the units seem to work out on that, and our conclusion is interesting in that it only really depends on the radius, which everyone's subject to, right? When you went to the fair, everyone's subject to the same radius. Coefficient of friction, that could have probably messed you up a little bit. I mean, if you'd had the Hugh Hefner silk robe on or something like that, you may have had some problems sliding down the thing. But most people with wool or cotton on or something like that are probably going to have about the same coefficient of friction. Yes?
With talking about the ride, wouldn't they still have to distribute the people according to their size, because you get really heavy people on one side and you get kind of a wobble?
Yeah, you're concerned about distributing the people is a good one, but probably from a practical sense in terms of getting this thing out of balance. If you have all of your heavy people here and all of your light people there, you could be out of balance. They're probably designed so that the weight of the people is pretty small compared to the weight of everything else. It would be unlikely unless you had, just this really clever group of really heavy people and really tiny people that wanted to try and make a problem out of this, that you could even get it to come up. But you are right. You are right. You'd have to worry about that in terms of this whole thing being out of balance. Hopefully you might design the thing, put an accelerometer on it. If it starts to shake a little bit like the washing machine when it's got a big blanket on one side of it, that it would shut itself down. Okay, so you
Put something heavy in the dryer.
yeah, same thing. Yeah. So where we'll go next time, we got to look at a car going around a curve and the implications of that, and that will pretty much finish our work in kinetics, and we'll go on and talk about some of these problems from a work energy standpoint. So that's where we'll head from when we get together next time. Take care till then.